My name is Gabe Silva. As he mentioned, I am from the data center platform team at Microsoft. Kind of a stranger here. I know it's out of the ordinary to have a Microsoft guy in a DPDK conference, but we've been doing some exciting work lately, similar to DPDK that I wanted to share with you, and we've been partnering with Intel very closely in making this technology PacketDirect work. So I wanted to let you guys all know this is all just a technology discussion. I'm not releasing any plans for the future. It's something we've been prototyping and playing around with. So just, I want to leave that out there. No plans, and there's nothing planned for any time. I want to go over a couple things first. I'm sure you're all familiar with the changes that are going on in the networking industry, so I'll kind of fly through those slides, give you just kind of the Microsoft point of view, how we're handling it. Next, I'll talk about what is PacketDirect, what it is and what it isn't. Then I'll jump into the architecture and how we approach this PacketDirect problem, similar to DPDK. Then the scenarios that we were targeting, and jump into future possibilities and what PacketDirect opens up for the Windows platforms. And then I'm going to attempt a demo. My Wi-Fi's been on and off, so at the end I'll show you guys a demo of PacketDirect working on par with what DPDK provides you in a Linux system. So first, talk about the state of the union, what's going on in networking. We are at an inflection point currently. Things are changing rapidly, and as the data center platform team, we are trying to keep up as best as possible. So we are noticing that we are moving things from the networking stack down to the NIC very quickly. The stack is getting lazy. It doesn't want to see packets anymore. We want to get them in and out as quickly as possible. So we are implementing more and more offloads and seeing more things so that we can minimize the CPU that we're spending on networking, as well as maximize the amount of bandwidth that we're using on the NICs. This in turn allows us to make more room for VMs on the system. Secondly, we're disaggregating the hardware. No longer are we looking at specialized hardware functions. With things like NFV, we're trying to move everything from that hardware into a VM. This is a trend that we're seeing more and more, and as Windows, it's something that we need to keep up with. And the next is silicon grows up. Another research item that we've been playing around with is merchant silicon, as far as getting silicon and opening up the interfaces so that we can control it in any way we can throughout the data center. So I'll jump to my next slide. So SDN is everything that we've talked about. So it's the vSwitch, it's NFV, and it's allowing us to actually move the data center in a very agile way. Now we can take full networks, tear them down, and bring them up within a matter of minutes. Next is the network function virtualization, NFVs. I talked a little bit about bringing up and bringing down these applications that were previously hardware. So we can now scale out rapidly or scale back in depending on the workload that the tenant has. And lastly, innovation and performance on merchant silicon. We all know that hardware is faster than software. Anything we do in software, we can always implement some kind of ASIC to make it faster. So if we can open up those interfaces on the existing hardware and use it to our advantage, we'll be able to see things like 40 gig load balancers, which is what we're trying to accomplish as we move forward, the most bandwidth that we can. So how does this translate into data center requirements? We're seeing most data centers adopting 10G. That's almost a given now. 40G is on the horizon, and we as Microsoft need to figure out how the stack is going to hold up against 40G. So we've been doing a lot of testing, looking at how many packets does it take to get in and out of the system? Can we do 40G with the systems we have out there? So on a regular box, you'll find that with the processing power we're given and the stack that we have, we can't accomplish 40G without a very, very powerful box. We're looking about 20, 25G is what we're seeing. And if we get a server grade box, we can crank 40G, but it's still, the stack is held up. But in the horizon, we see things like 100G. How's the stack going to hold up against 100G once those NIC comes out? So we're doing a lot of investigations now to make sure that Windows Server and Windows are future-proof. Next, in the data center, you don't see the latencies that we're used to as a client OS. In the data center, you see anything from 1 to 2 milliseconds, and 2 milliseconds is slow. So you usually see 1 millisecond, if not less, in the microsecond range. Lastly, DPDK set a standard of we want to see as many packets per core as possible. We want to get them in and out, and it's something that we realized when we try to do things like NFVs. So we realized there was something that we had to do, so we investigated our stack and really scrutinized what it is that we were doing. Our stack is a general purpose I/O. So we try to support things from Bluetooth, regular Ethernet, Wi-Fi, things that data centers don't really have to worry about. So when we think of networking, we have to think of both client and data center. Even though I'm on the data center team, I take a lot of client requests for Hyper-V, for the TCP/IP stack, and at the same time, I'm also trying to tune the stack for things like the data center, 40G, 100G, and latencies in the microseconds. Another thing we noticed was the stack is driven from the NIC, from the bottom up. So the NIC decides the context in which your application is going to run. You have interrupts, which provide lots of overhead. The application doesn't get to control where the interrupts go, nor does it get to control the memory. The NIC is always allocating its own memory and passing the buffers up. So we looked at the stack and we came up with the conclusion that it's not going to be enough for us as we move forward. We took a look at the ecosystem, and we have done things like Rio in the user space before that has all the same concepts that you'll see in things like DPDK. It just hadn't been moved down to the hardware. So we decided we can do better. We can give the application control of its own destiny. We can let the application allocate its own buffers, decide the filters that it wants to process on the NIC, and what queues are indicating which packets, so it doesn't have to do those lookups. So holistically, we saw DPDK, and it was a proof of concept for us that, hey, what we're doing in software is working on hardware. It has a huge following, you guys, and we decided to do something about it, and we partnered with Intel and came up with PacketDirect. So what is PacketDirect? First and foremost, it is not replacing our current data path or current I/O model. PacketDirect is meant to run simultaneously with the same NDIS, NBLs, and data path. It's not something that we think today is a future. We think it is something that is application specific, data center specific, when you're looking at things like software load balancers, DDoS inside of the VM, or firewalls. So it's not going to replace what we have today, but rather complement. So if you have a large load VM that you need 40 million packets per second, 10 million, 20 million packets per second, you can switch PacketDirect on if you have a capable NIC, and your VM will then just run. So that's kind of the vision we were looking at. And even though we're in a virtual world, we wanted to look at physical and virtualization. But we kind of had constrained resources, so our main goals when we were designing PacketDirect was around the virtual space. We were looking at things like vSwitch. How can we make this run inside of the VM? How can we take advantage of current technologies? So physical was interesting, but there was a lot that had already been done around physical that we could model after. So we took a look at virtualization as our primary goal. We wanted to see how we could get packets in and out in a virtualized data center environment as quickly as possible and really maximize the packets per second. So we took a look at a lot of appliances inside of a VM. We had a DDoS, a firewall, SLB, just things that really need to crank packets as quickly as possible and doesn't need specific hardware. So now I'm going to jump a little bit into how we designed PacketDirect. And if you guys have questions, feel free to jump in at any time. More than happy to answer them if you guys want to make it kind of more like a Q&A. So the inner workings of PacketDirect, there's three main components to our design. The first was the mini port. So the NIC actually has to implement a driver. But the advantage of this is it only has to implement the driver aspect. We found that most NICs today had the capabilities that we needed. So there are no hardware changes needed to implement PacketDirect. It's just an upgrade of the software. You just install the new mini port and you should be able to run with it. We've been working with the Niantic, and I've been going through many iterations of the driver. So it works just fine on the Niantic, Twinville, and we're even working with Intel to get it working on Fortville. Today my demo will be on the Niantic. So that's the provider interface. Once you have the provider interface, we actually implemented a platform that does things for the client. So, and the client is the person who takes advantage of the hardware queues and everything on the NIC. So here's a little picture of the architecture. It's kind of what I just described. You have your PD NIC, which has an NDIS mini port, and that mini port is now PDPI aware. So here's your traditional NDIS stack, running through the LWFs, LWFs, WFPs up in the protocol drivers. And here's your PDPI PacketDirect interface. You'll see that a lot of the overhead is actually cut out, because now the stack isn't doing things like RSS. That's something that we will leave up to the client to decide how they want those packets to be processed. By plumbing down filters, you don't have the 4-tuple filter. You're not constrained by that anymore. You can decide where you want your packets to go by plumbing down the filter that you want to use. So if you want to use a 4-tuple, that's fine. If you want to use a specific IP, destination or source address, that's also fine. We have a large number of possibilities for filters, and a lot of the NICs already support it. So it was very easy to just take advantage of the capabilities of the NIC. So it's a much skinnier model than what we have today with our traditional NDIS path. And you'll see we'll have a kernel mode PD client here, which actually takes advantage of the hardware capabilities directly, rather than having the PD or having the NIC tell it where it wants its packets to be processed. So there's a couple concepts that we have that are specific to PD. The first is an execution context. What an execution context is, it's a thread that's constantly pulling on a processor. Sound familiar? So constantly pulling, and the client is controlling its own destiny. The client will tell the PD platform, I need 1 execution context, I need 2, or maybe 3, depending on how many cores you need to process that traffic. But all it is pulling, and it's doing this post and drain functionality, which I'll get to here in a second. The next are PD buffers. So I don't know how familiar you guys are with the Microsoft stack and Microsoft networking technologies, but we use NBLs. And net buffer lists are made of net buffers. Net buffers are made of MDLs, which are just memory descriptors. So there's a lot of layers of indirection there. With PD buffers, it's just one layer of indirection direct to the memory. So we wanted to cut out as many cycles as possible when doing lookups for the memory and being able to get directly where we needed to go. The next is the filters. So the filters are kind of a big deal because you can plumb down the exact packets you want, and the NIC will indicate those to you directly. So all you have to do is look at a QID, and you know exactly what it is you want to know about that packet. And then you can process it on the execution context that you'd like. So if you have the 4-tuple we were talking about, a 4-tuple goes to your first execution context, and that execution context doesn't have to do lookups, it doesn't have to find it, because it already knows where it's coming from. Last is the post and drain capability. And all post and drain does is it's a very tight-knit loop. You're posting packets to the queues on the hardware NICs, and what that's doing is you're receiving packets. If there's any packets there that are completed, we'll pull those out of the NIC and replace it with a new PD buff. And if there's any that need to be transmitted, once it's transmitted and completed and marked as completed, we'll pull it off and replace it with a new PD buff. And so that's the post and drain capability. So the PD provider, a couple more details on that. It's implemented by the hardware. So we work closely with Intel when we were developing these APIs and kind of trying to figure out what we were going to do with PacketDirect. And they helped us mold what our APIs were going to look like. So we got real feedback from them as we developed it, just to kind of see if this was a proof of concept that we can make work. And the Niantic, you'll see today, we have a working prototype, and the Fortville is soon to come. So 10G is actually pretty cool to see, but you run into hardware limits on those NICs, so as to how many packets you can process per second. It'll be much more interesting on a 40G NIC to see how many packets we can get on just one core. So today with our traditional Endus stack, we got roughly about 1 million packets per second. And if I can get the demo up and running, you'll see that we are doing about 13 million packets just sending and receiving. And with the simple L2 forwarding, we can get about 11.6 packets. And this isn't a fully optimized version of the NIC yet. We've been iterating and iterating, and so we believe that we can still crank out a lot more. We think this is just the beginning. So what the PD provider is actually doing underneath the covers is it's giving you access directly to the hardware queues, the send and receive queues and capabilities of the NIC. So before, with VRSS, VMQ, the NIC would do all that for you. It would bring up the queues, tear them down when you wanted to move them. Today, you're in charge of all that with PacketDirect. You get to tell the NIC when you want to create a queue, what filter you want on it, whether you want to do RSS or spreading, or whether you want to do some kind of VMQ spreading on it. It's completely up to you, and the NICs have the capability to support this. And the PD platform actually communicates between the client and the NIC and does the following for you. It does the buffer management. So when you tell it, hey, I need to allocate, as a client, I need to allocate buffers. I want 2 megs of memory and cache. It'll go ahead and pull that out in the system and have it there for you. It does the queue abstractions, so the client doesn't need to know what a receive or send queue is. It just needs to know what the functionality is. Tell it, create me a receive queue, create me a send queue. I want 4 receive queues, 1 send queue. Next, it does the management and diagnostics for the client. So that way you can tell how many packets per second are coming. If your filter's off, we want to make sure that you can tell and diagnose issues quickly. And the client is exactly that. It's consuming our PDPI platform and going through the platform, and everything is kind of abstracted away from it as far as what the platform does. But it does take advantage of the new I/O model. You can think of it as a network service or application. All it has to do is make a call, and today it's implemented in kernel mode. So we don't have a user mode PD as of yet. And makes a call, it opens up the provider on the NIC, it passes back its dispatch table, and from there you're able to use all the functionalities on the NIC as you would a regular client. So the biggest thing here is the client then owns its destiny. It owns all its execution context. It tells the system exactly where it wants to receive, when to send, and is in charge of its own destiny. So a scenario that we had that was really important to us was making the vSwitch PD capable. It's something that we have been testing and playing around with. I'm not showing that today, unfortunately. Today is going to be just the physical raw capabilities of PacketDirect. We ran a little out of time, but it's something that we think is very important. Being able to get packets in and out without an SRIOV capable NIC of the VM as quickly as possible. So you'll see here we have our data center and internet. It exists simultaneously with the Endus path. You have PacketDirect provider. There's nothing stopping you from having more than one provider. There's nothing stopping you from having more than one PD client. So here you can take multiple clients depending on what it is what you want to do. Here I just have a site-to-site gateway that we have inside of our VM. And that's something that we've been trying to play with. Don't have it completely sketched out. We have other priorities, but this is definitely something that we are interested in moving forward in the future. So let me see if I can get this demo up and running. This is going to be the interesting part.
You need the cable into there.
Yeah, let me see if I can find a sweet spot in the room first. All right, guys, this is going to be an exercise on Wi-Fi. Okay, can I steal that cable? Yeah.
We'll see how long it goes.
Ooh, I can sit.
They're going to end up being a couple feet short, I think.
That's fine. Okay. Perfect. Okay, I'm just going to sit here and make myself comfortable.
That's better than kneeling.
Yeah. All right, guys, so I have 3 machines here. I have a sender, a forwarder, and a receiver. So my sender right now is empty. I'm going to try to do 2 demos first. The first thing I'm going to do is I'm just going to do the raw sending and receiving. So I have a SendDirect script here, and what it's going to do is it's actually, let me see if I can get it going. What it does is it opens up a PacketDirect provider. Ooh. Hold on one second, I only want one of these up. Okay, so it opens up a PacketDirect provider, and it's just a tool that we created. It's a tool that exercises all the functions we have within PacketDirect. And it's connected to the receiving machine. So right now I'm only seeing 7 million packets. I think that's because I opened both at once. But you'll see our receiver is actually getting 13.4 because I believe both were open for a amount of time. But 13.4 is roughly what we see. Let me see if I can get that on and off again so we get the correct results here. Oh, come on. Let me close this. Since it's just a prototype driver, I need to reset the NIC every time I open up a open a PD provider. I'll try clicking. Okay, here we go. So hopefully we'll see this ramp up quickly. Oh, I should have showed you guys a zeroed out counter over here. So here we have a receiver, and it's receiving roughly about 13.4 packets per second. Now, that's not quite 10 gig. It's actually small packets. We're using 60-byte packets, come to 64 bytes, which is the smallest packet you can get on the wire. So this is the just plain sending and receiving. And what you'll see here is on our sender, we have one core that is completely utilized, and that's just from the polling. So when we're polling, we'll see that even though we're transmitting about 13 million packets per second, it still has about 99.3% empty iterations when it's actually polling through and it's trying to send packets. About 99% of that is empty. So we're hoping to take advantage of that and be able to crank out more as we reach speeds of 40G and 100G. Now, if I close this out.
So is that on one port or two 10 gig ports?
Oh, this is on one port. Yeah. So it's one port, one core. Now let me restart my NIC. And I'll show you guys the zeroed out counters here. Although you'll see that both cores here are still just trying to get packets as quickly as possible. Now, our receiver on the other end is going to get some action because we're going to go from the transmitter to the forwarder to the receiver. And it's just simple L2 forwarding. And so through the transmitter, we can actually get 13.4 million packets. That doesn't change. What changes is the forwarder. Here, the forwarder can only handle about 11.4 million packets. So we're looking at it, and we're still improving and investigating bugs. But we're getting 11.4, and it's actually reaching the receiver. So 11.379 packets per second. And again, this RX PPI is just the number of packets we're trying to pull every time we're doing a post and drain. And then the empty over here, the receiving empty iteration percentage, is the number of iterations that we do that are actually empty when we're trying to pull and there's no packets there. All right, guys, and that's actually all I had. So let me jump back into my.
Did you have pause frames on when you were running that?
Did I have, excuse me?
Pause frames
No.
on? Okay.
No.
Let's switch back over your last couple slides.
Yeah, and I have a couple more slides here. Just finish up. Yes.
What was the processor that you ran? I know it was an E5 2660 or something.
Ooh, I don't know, but I can look it up quickly for you if you'd like.
And when you say core, is it one physical core or is it a core, a virtual
No.
a thread?
We don't use threads. So we always use physical cores. When the end-of-stack actually looks for cores, we don't pass back hyper-threaded cores. And that's for the offloads. So things like VRSS, VMQ, RSS, they never use the hyper-threaded cores. We only use the physical cores. Okay. And I think I left it over here. Okay, so today we can do about an order of magnitude better than what we could do with the traditional end-of-stack. We're really excited with it. We know there's a world of opportunities out there, what we can do. We've kind of seen the DPDK community, and we want to grow something like that for PacketDirect and the Windows platform. And we're looking ahead and looking at things that are actually kind of funny. I got the schedule for today, and I noticed there were actually things on there, what we were looking at as well. Making PacketDirect work with SRIOV. If you implement it inside the VM, what's stopping it from plumbing down queues or working side by side with SRIOV? Next, it's making PD publicly available. We have no timeline. We don't know when we'll actually have it out, but it's something we're working on doing and integrating it into the platform. We'll see if it makes it. Next, PD inside the VM, again, working with SRIOV. Really interested to see the kind of results that we can get. And lastly, a user mode PD. I know things are out there already for other platforms. There's third-party solutions, but what if we could bake that into the Windows platform?
So you said future possibilities PD being publicly available.
Mm-hmm.
Are your data center services like Azure, Bing, Office 365 using PD today, or do you have plans for using that independent of PD becoming publicly available?
They're very interested in using it. They've been one of our partners as well. Intel works very closely with our Azure teams, and so as we've been cranking out builds, they've been looking at them and been following our progress very closely. So you can imagine that they're very interested in incorporating this into Azure and have talks with them very, very frequently. So, but as of today, no. This is just a proof of concept, just barely getting the driver up and going. Spent some time this weekend making sure that it was there. So as you can imagine, it's still in a pretty rough state. Any other questions?
Can you talk a little bit more about the SRIOV scenario? In your case, you were running on top of a hypervisor. So this will be assuming running on top of a hypervisor?
Yes. So we'll still be assuming the hypervisor because you need to, SRIOV goes to a VM, right? So I'm not sure how other implementations of SRIOV works, but we would still have to plumb down the filters and everything from the VM to the NIC, so that rather than doing spreading based on RSS like we do today, we'd be able to plumb down the custom filters from the VM to the NIC. So that's how we're imagining it working. We don't have any kind of implementation yet, but we still have a couple things to figure out before we do SRIOV and move it that way. Again, things like in the VM is going to be very interesting to see how we can accelerate the path into the VM and then accelerate the path inside of the VM. So they're two completely separate paths. How the hypervisor is going to handle as that many packets running through both.
So along the lines, any plans for PD? Any plans for PD over the virtual NIC that you have in Hyper-V Guess?
That's what I was just talking about.
Okay.
So it's not plans. Nothing that we have today is plans. It's something that we're looking into. And it was a natural progression from having PD on the NIC in the physical host as to putting it in the NIC on the vNIC or the VM NIC, seeing how PD would perform there. We ran out of time. Otherwise, we would have we're trying to get something up for the demo today. Because we really think the virtualized environment is where this is going to really shine.
I'm not that familiar with the Windows architecture, but before the PD, was it poll mode, or was it, like, poll mode is also one of the new aspects to this?
Poll mode is a new aspect, yeah.
So
It was
poll
always-
mode-
the networking's always been interrupt based in Windows platforms.
Okay, so you went to poll mode. What about huge pages? Is that something you picked up as well?
We have, I believe we have the ability for huge pages already, but we want to make it much easier to use with PD. So it definitely is something we're looking at with the memory allocations.
Have you ever considered that extra cost? I mean, you showed that percentage of cycles doing nothing. I think, what was that? One of the little parameters, that the KPIs you had there, was when you're polling and you had nothing to do, and I probably went back to sleep.
No, it actually did not go back to sleep. You continue polling.
Oh, sorry.
Yeah, when the prototype, you continue polling. We don't have
Continue.
anything, I don't know if you guys are familiar with RDMA. RDMA has a notion of arming, right? So if you don't see interrupts or packets for a certain amount of time, you put the NIC to sleep, and then it'll send an interrupt. So we've looked at some hybrid models as far as do we poll for how long, and if we don't see packets or we have so many zero iterations, do we put the NIC to sleep and then request an interrupt once we get packets again? Those are things we're looking at, and nothing we've implemented yet, but definitely concepts that we've thought of and thought it's already present today in RDMA. Just something that a thought we've had to bring it over to the PD platform as well.
Yeah, that was exactly what I was going to ask, because that cost of that core spinning and that power consumption, have you considered that as well?
Yeah, and that was something that came up immediately with the other properties. So if you have an Azure and a Bing, they can't afford to be spinning on a CPU all the time. So you have to find a way to solve that problem. Otherwise, this goes nowhere. All right? Any other questions?
Question in the room about the CPU, it's a Sandy Bridge.
Sandy Bridge? Thank you. Thank you, Richard. Go ahead.
Did you say you have the mini port driver and the PD driver both controlling the NIC at the same time? In one of the pictures, one of your architecture diagrams.
No, so the mini port is actually giving the,
Right, is that right? No, not the one, sorry. Yeah.
so no, they're not control. The mini port's just giving its capabilities to the client. So the client here is using the mini port to access the hardware queues. Those queues would not be used by the NIC to indicate interrupts or anything else that would go through the NDIS path. Right? Is that your question?
So my question was, can you still have regular applications going over your NDIS protocol stack?
Yes. That was a top priority for us, is to have both working simultaneously.
And how would that work as far as interrupt mode versus poll mode? So if PD relies on poll mode and many port is interrupt driven,
then you would have two separate sets of processors, one for your PD, another for your RSS or VMQ that's happening on your NDIS mode. Does that make sense?
well, yeah, but could you put your NIC in, like,
Yeah,
some
so the mini port would know, so what happens with your NDIS stack is going to happen on a certain set of processors, right? And that's controlled by the admin. The admin plumbs it down. And so your admin and the PD application would have to be aware of one another so that they don't stomp over the other one's processing. We haven't explicitly put anything in the system to say, hey, you can't do that, but it's something that that we know we have to do. So there'll be 2 sets of processors for your PD and another set of processors for your traditional NDIS path. And it'll be up to the administrator to decide, I want this many processors for my PD buffers, and I want this many processors for my NBLs coming in. Right? So if you, and that's up to what you're running in the workload in the box. If you're running an SLB, you're going to allocate 3, 4, 5 queues to your SLB and leave 1 or 2 to process just the noisy traffic coming in, your ARPs. And
but if a NIC is getting access through your NDIS port, then the PD will not be touching that NIC, right? That particular NIC.
It will. It will. So you can have 2 different set of queues on that NIC. You can have the NDIS queues and you can have the PD queues. So your PD client will be polling on your PD queues, and that's what the NIC shows to the PD client. It would never show an NDIS queue to a PD client, because then it would assume it's getting interrupts and it'd bug check immediately.
Just a quick question regarding the pull mode drivers. So people concerned about the CPU polling because actually in the Linux domain, those are so-called NAPI, so kind of solve the problem a little bit.
I'm sorry, what?
NAPI.
NAPI, I'm not aware of NAPI.
So go back to the driver side. I think in your case, you able to use in PD, you're able to modify the driver a lot, or just what kind of proportion of code change in order to make this PD part work?
It wasn't a huge change. I know that I can't speak for the IHVs themselves. The vendors have done those changes. I don't think it was anything significant. To get the prototypes up and running, it took a matter of weeks, not months.
Okay, thank you.
Yeah, no problem. So yeah, it really wasn't too significant of a change. And actually, when we approached vendors about this technology, most of them were quite pleased. Intel said, we can already do this. Like, let's jump on it. It's DPDK, right? So let's see what we can do and run with it. So it was actually quite easy. They were very eager to work with us and us them. So next step is very excited to see what we can do on the Niantic, on the Fortville, the 40G part, and keep moving forward, chugging along with 40G and then 100. Any other questions?
Did you actually profile and find out where the bottlenecks were? Was it sort of descriptor handling, NICs?
No, we haven't. No. We got this up to a state that where it was working, and we kind of ran with it. I have certain steps to follow. And actually, there's a couple things I want to try, and as soon as this is done, I'm gonna try both the send and receive and the forwarding at the same time, and just to kind of see what the system does. It's very much a work in progress, but something we're looking forward to finishing up.
Yeah, hi. It's just now you mentioned it's the 40 gig throughput for the VM, but I'm not sure right now. It's I heard it's the most of requirements for the VM throughput is 10 gig. Have you seen the 40 gig requirements for the virtual machine?
No, for a virtual machine, no.
But I saw one slide. Is maybe I misunderstand.
So 40G is in the horizon. A lot of vendors are coming up with 40G parts. Intel, for example, the Fortville is due out very soon. I'm not exactly sure when the release date is, but it's something that oh, it's today?
Yeah.
Congratulations, guys! It's out today.
You gotta be a day ahead of the iPhone 6, right?
So I know we've been doing a lot of testing on 40G parts. 40G to a VM, we've seen on very powerful machines. Nothing that you would see in a standard data center. It's something that we are looking forward to. 10G right now seems to be the standard. And even then, 10G, there aren't a lot. It's dominant in the data center, but when you move to enterprise, there aren't a lot of enterprises doing traffic that actually fills the 10G 10G pipe. You see workloads of like 2 or 3 gigabytes. I don't know how many of you guys are familiar with VRSS. It's basically just enabling RSS inside the VM. So we can get 10G pretty easy to the VM, but there hasn't been a lot of cases to use it. Some large file servers, SQL workloads, but other than that, I haven't seen a whole lot of 10G. We're just trying to stay ahead of the curve and waiting for the 40G parts and making sure that we work well with the 40G parts and enable the scenarios that need to be enabled to make the data center run smoothly and to take advantage of things like the NFVs, because the networking model we had today just wasn't cutting it. Yep.
Have you considered porting DPDK to Windows? And if yes, are there any reason you did not use DPDK itself?
That's a loaded question, but but we decided that PD was the way to go. We've looked into DPDK, and like I said, there's a large ecosystem here for DPDK, and we wanted to try to take advantage of that. And so we're looking at ways to make them work. Just right now, no, they're both two separate entities. PD is PacketDirect and DPDK is DPDK. They're different interfaces that Intel has just coded to. They've made their NICs work with our PacketDirect as well as DPDK. So.
All right, Gabe, thank you very much.
Thank you.